A-Level Maths, Mock Paper 3, Question 4. This question mentions normal distribution right at the beginning. It says time taken to complete a call to the call center may be modeled by a normal distribution. And it gives you the mean, 16, and it doesn't give you the standard deviation. The very first question for 3 marks is to use the fact that 10% of calls take longer than 22 minutes to calculate the standard deviation. The first thing to remember about this is that the calculator gives you information that lets you work with the normal distribution. But of the 3 options that it gives you, only 2 of them are worth paying attention to. The first one, normal PD, gives you the height of the curve. It does not give you the probability. For the probability, you need the area between 2 limits. That's what normal CD gives to you. So for instance, if you had the average height of males 178 centimeters with a standard deviation of 8, you could work out the probability of a randomly selected adult male being between 180 and 190 centimeters. You would use normal CD. You put in your lower limit of 180, your upper limit of 190. Your standard deviation comes first. Be careful with that. Don't put in 178 before the 8. And the 178 is the mean, mu, and out pops your probability. Inverse normal, on the other hand, you may also use, in fact, you will need for questions like this one. Inverse normal requests an area, and you'll also need a standard deviation and a mean. So if I were to say, for instance, this says 10% of calls, if I put in 0.1, it gives me a number that's quite small. So if I was thinking, well, I wonder what height the top 10% of adults would be, this number isn't going to give it. In fact, this number is going to provide me with the height of the bottom 10%. So if you are as short as 167.7, then you're in the lower 10% of adult males. To get the top 10%, you put 0.9. In other words, that number that we give to the inverse normal as an area corresponds to the area below a certain point. We're assuming there is no lower bound, and we're asking the calculator to give us the upper bound that corresponds to that probability. So that's what we're going to do here. But there's a slight problem. If they told us the mean and the standard deviation, we could use normal CD to work out the probability of a call taking longer than 22 minutes. Or we could use inverse normal to find the time for which 10% of calls take longer than. In other words, 90% of calls take less than this time. But we've been given both of those. What we haven't been given is sigma. We've been asked to calculate the value of sigma. The way that works is by using something a little bit sneaky, the standard normal distribution, usually known as Z. Z is a normal distribution with a mean of 0 and a standard deviation of 1. And we can calculate things like the probability that Z is less than some value equal to, well, the top 10% of calls take longer than 22 minutes. So I'm interested in what proportion or how extreme a value needs to be before it has 90% of the data below it. And you're going to see how this standard normal distribution helps us with our question. When we go into inverse normal, we put in 0.9, but for our sigma, we put in 1, and for mu, we put in 0. 1.28 is not just a number, it's a number that corresponds to the number of ones above 0, which in this context is equivalent to saying the number of standard deviations above the mean. So inverse normal tells us that 0.9 the point below which 90% of the data lies is 1.28 something standard deviations above the mean. And crucially, this is true regardless of what the situation was. If I change the standard deviation to 10, you'd find this turns into 12.8. It's still 1.28 standard deviations above the mean. What if the mean was actually 1,000? Then instead of 12.8, it's 1,012.8. It's still 1.28 standard deviations above the mean. If I change my 0.9 to a 0.1. Now I've got a negative number. This is 1.28 standard deviations below the mean, but it's a lot easier to see if instead of using 1,000 for the mean, I put in 0, and then it's a negative number, therefore below the mean. And how far above or below the mean in terms of how many standard deviations is easier to see if we set the number of standard deviations to 1. So that's what we're going to do here. We've got 90% corresponding to 1.28 standard deviations. Therefore, we can say that that 22 minutes that they referred to, 22 is equivalent to the mean plus 1.28 standard deviations. And you'll notice this is just a linear equation involving mu and sigma. If they'd given us a second piece of information of a similar type, like 10% of the calls take longer than 22 minutes, 30% of the calls take shorter than 10 minutes, you could use the second piece of information to get a second equation and solve simultaneously to find mu and sigma. In this case, however, it made life a little bit easier for us by telling us the mean is 16 minutes. That means 22 equals 16 plus 1.28 sigma. And we can just do a quick calculation back in calculator mode. 22 minus 16 is 6, divide by 1.28, and we get an answer for our standard deviation, 4.6875. 4.69 to 3 significant figures. Now, what's gone wrong? 4.6875, and they've got 4.68. The issue is, I played fast and loose with my rounding too soon. 1.28 is correct to 3 significant figures, but if I use a value that's only correct to 3 significant figures, I'm not going to get an answer at the end that's necessarily correct to 3 significant figures. What I'm going to need to do is take that 1.28 that I worked out before and get a more accurate answer for that, a greater level of precision. So I go to inverse normal, I put in 0.9, and it's not just 1.28, it's 1.28 something. If you want to be really precise, you store that number somewhere. I'll store it as x. And then when I go to my calculator mode here, and I do 6 divided by that number, I should get a much more accurate answer. So now all I need to change here is 1.28 something sigma. And when I round, I get 4.68 to 3 significant figures. And I can be confident I've got it right because it was a show that question. For part B, calculate the percentage of calls that take less than 13 minutes. It's a 1-mark question. So if the time taken to do a call, probability of that being less than 13, that's equivalent to saying effectively no lower limit and an upper limit of 13. We can get that from normal CD. So option 2, we put in just a massive lower limit. You can put in 0, probably that'll work fine for most things, but in this case, play it safe and go very, very far below. Upper limit of 13. We now have 4.68 for our standard deviation, and we still have 16 for the mean, 0.26. It doesn't specify a level of precision here, so I'm going to write this as 26.1%. Stick to 3 sig figs. That's what they did before. Okay, the next bit is the meaty part of the question, 6 marker. The supervisor claims that the mean call time is less than 16 minutes. Remember, 16 was the mean that they gave us before. He collects data on his own call times. Now we have 2 pieces of information. We can say that the supervisor's call times are normally distributed. But remember, when you set up a normal distribution where you don't know the mean and the standard deviation, we can still refer to them like this. X is normally distributed with a mu and a sigma, and the information I do have about X is that the probability of X being greater than 17 is 20%, and probability of X being less than 8 is 10%. It tells us 20% of calls take more than 17 minutes, 10% take less than 8 minutes. Now, having 17 as a lower bound is not so helpful for me because I want to be making use of inverse normal. So I'm going to change this one around a bit. probability of x being less than 17 must be 1 minus 0.2. If there's a 20% chance of having calls that last longer than 17 minutes, there's an 80% chance of having a call that lasts less than 17 minutes. Now we just need to take the 0.8 and the 0.1 and figure out how many standard deviations above the mean those correspond to. And I can do that very quickly from the standard normal distribution. How many standard deviations above, possibly below the mean does a probability of 0.8 correspond to? And we go to inverse normal. We put in the 0.8. We put in 1 and 0 for sigma and mu. It gives us 0.84 something. Well, I'm going to use 4 decimal places, 0.8416. And for the 0.1, it's very quick. We go back by pressing equals. We change the probability to 0.1. We get a new value. This is negative 1.2816. Therefore, we can now say, remember this one corresponds to the 0.8, which corresponds to 17. So the value of 17 is 0.8416 standard deviations above the mean. We just do the mean, mu, plus that many standard deviations. And then the next one was 8. The value of 8 corresponds to the lower limit, the upper limit of a 0.1 area. So 8 must be 1.2816 standard deviations below the mean. That one's got a negative in, so minus 1.2816 sigma. This is like what I was describing shortly before. This is 2 equations in 2 unknowns. By far the quickest way to do this, I think, is to jump to menu option A on the calculator, select simultaneous equations, choose 2 unknowns, and then I'm going to read these as if they're the other way round. So I'm going to think of it as mu plus something sigma equals 17. I just need to remember that in this context, mu corresponds to x and sigma corresponds to y. 0.8416 and 17, 1 minus 1.2816 and 8. If you get ludicrous numbers from this, you should be able to check that they're ludicrous and identify where you've gone wrong. It's easy to go wrong with this, but it should be usually relatively easy to check as well. So I get mu equals 13.4. Sigma, which should be my y value, comes out as 4.24. And that's encouraging because the original situation that was being described in the call center was a mean of 16 and a standard deviation of 4.68. We're getting practically the same standard deviation, 4.24, but we're just getting a slightly lower mean. In the final part of the question, this sounds like a lazy version of hypothesis testing, state giving a reason whether or not the calculations in part C support the supervisor's claim. You can tell that you don't have to do a full-on hypothesis test by virtue of the fact that they haven't given you a significance level to use and they haven't said stating your hypotheses clearly, which they usually do with a question like this. Also, a bit of a giveaway, it's 1 mark. So they want you to demonstrate that you understand the concept of hypothesis testing without having to go through the rigmarole of actually carrying out a complete process, which means you need to do some sort of sensible comparison between the values you've found and the previous ones. So at this point, compare the 13.4 to the 16. And if you've managed to make yourself a diagram, which is usually a good idea with these situations, then it'll help you because you'll have some sense of whether your numbers are reasonable, within ballpark. This will be my standard diagram for the previous part. A mean of 16. If you go up or down by 1 standard deviation, you get to these 2 inflection points. And remember, roughly 15 or 16% of the data lies below this point. Roughly 15 to 16% of the data lies above this point. That means that when you're looking at a value like 13.4 and considering where that would lie on here, it's Not quite as far as one standard deviation below, but it seems to be a significant distance along the way. So yes, potentially it lies within the acceptable range of, you could get a number like that for a single data point, but we're dealing with an entire other distribution. We're talking about a bunch of data this person has collected, and the mean is not just similar to 16, it's some way below. So it seems to support his claim. I'd be tempted to write here something along the lines of, since the mean is significantly lower, this does support the supervisor's claim. The standard deviations are not massively different, so the shape of the distribution will be the same. There's evidence that we're still dealing with a similar sort of range, similar variation. 4.24 is similar to the 4.6 something we had before, but the mean is lower. We can check on the mark scheme, and you can see they're not asking for a huge amount of detail here. They're saying that the mean is less than 16, so that supports the supervisor's belief. We don't have to justify whether it's significantly below or how far below it would need to be. To get that sort of information, you need more data. You need to know exactly how much data the supervisor had collected for a start. But this is enough to say, yeah, it seems to be on the correct side of the 16 to what he will be anticipating. For the rest, you can see that they need evidence that you've used a sufficient level of precision here. So the 1.28155 something. They give a mark for finding that value, and they give a mark for the final answer in part A. Notice that the method they often use in the mark scheme involves this subtracting the mean and dividing by the standard deviation. You can use that if it makes sense to you, but I think the idea of using inverse normal to find out the number of standard deviations above or below the mean is probably a bit more intuitive for most people. So that's question 4.